like to welcome you to this year's CESS 2011, brought to you by Catherine Nod and myself, Michael Way. We've all made it in fine today. I thought I would start out with just a few slides to give you some background on why I am into these workshops so much and what drives me to keep doing them, even though it's quite a lot of work, as you can imagine. So my favorite example of this is what I call Gaussian process regression, at least a project I worked on many years ago. It started out by giving a talk to the Intelligent Systems group at NASA Ames many years ago, where I talked about this problem of calculating redshifts for galaxies, knowing the colors of galaxies. It's a well-known problem, and Tomas Budovari tomorrow will talk to us a little bit more about it in detail. But in essence, this came down to a project I did with Ashok Srivastava in the Intelligent Systems Division at Ames. Ashok essentially had been using this problem to predict AVHRR channels from MODIS channels. AVHRR was an instrument that was quite a bit older for doing Earth remote sensing from orbit, and MODIS was a later instrument with more channels, and he was able to develop this training method technique for predicting channels using something called Gaussian process regression. I gave a talk to Ashok's group about this many years ago, and Ashok said he thought that this problem could be used equally well for this astrophysics problem. So we had quite a bit of success with that project. We published a paper, but then we came up across a problem where we had to invert some very large matrices. Now, by very large, I mean, say, 10,000 or 100,000 by 100,000 type matrices. So that seemed like quite large to us. I gave a talk in my branch to my division many years ago about this project, and my branch chief, he asked me, he says, well, how big are these matrices again? And I said, oh, you know, like 100,000 by 100,000. And he said, well, that's nothing. In quantum chemistry, we have gigantic matrices so big they don't even fit on disk, billion by billion type matrices. We said, wow, okay, wow, all right, so we should use some of those methods. So he gave us his method to try out. We tried to get it to work for our matrices, but we couldn't get it to work. We couldn't invert these very large covariance matrices, which were a byproduct of this Gaussian process regression. Well, it turned out that these quantum chemist matrices are very big, but they're extremely sparse. We have the completely opposite problem. Our matrices are absolutely not sparse. So, so we had this problem. So we also have a collaboration with some people at San Jose State in the mathematics department. And I gave a talk there on this problem and mentioned that we had this problem inverting matrices. Well, they had some linear algebra people there that were quite talented, and they decided to do a project with some students, which is often done, where they come to us at NASA and ask us if we can dream up projects for them to work on with us, and this was a perfect project, they said. So this is a group that I hadn't known much about beforehand, and I wouldn't say is world famous anyway, but they did a fantastic job of inverting these matrices for us, and it ended up pushing the method to the next level and making it incredibly useful for predicting these photometric redshifts. So my point of bringing up this story is that these kind of collaborations, these kind of local collaborations between different types of domains are potentially very fruitful. And all of us work in institutes where there are computer scientists nearby, or earth scientists, or space scientists. And one of the things I want to do by this, one of these workshops, is get people to realize that this is the way of the future and the present, and that we should work more together. We should go and visit each other's departments and give talks and try to find ways to work together to explore new avenues of collaboration. Okay, another serendipitous thing that has happened in the meantime, though, just last week or 2 weeks ago, Science Magazine had a whole issue, or part of an issue, related to dealing with data. And a lot of what we're going to talk about is dealing with data. And one of the things I really learned from this is that we really should have also invited biologists and chemists. If you just think about microarray data alone, that could be highly leveraged. They have tons of tools for doing regression analysis and all kinds of other things that we could use. Now, what's more embarrassing about this for myself is that I should have known this from some years ago, because Rob Tibshirani, Trevor Hastie, and Friedman at Stanford, they came out with a book, my gosh, it must be at least 5 or 10 years ago, called The Elements of Statistical Learning. And a colleague and myself at Ames, the astronomy group, we decided to go to this workshop that they had held, a 2-day workshop on this book. And 95% of the people there were indeed biochemists, essentially, going to learn these new techniques. And we were just a few of the smattering of the 5% of other disciplines, an audience of maybe a couple hundred people that were there. So I should have known that from this, before I even read this issue, that biologists and chemists would be good people to collaborate with. What I did not learn, of course, is that we all have data challenges in all different fields. I mean, computational challenges, storage challenges. They talk quite a bit about data standard issues. Visualization, how do we do visualization? Climate science, genomic data, ecology, etc. And they also reference this, this famous book, which you can download as a PDF from Microsoft, called The Fourth Paradigm, where many of these things were also discussed. I can highly recommend reading some of those contributions in The Fourth Paradigm. But of course, I have to show one of these giant data plots showing how worldwide climate data is expanding rapidly. Here you see model data, here you have satellite and radar data. Of course, in situ data quite flat, and you can see, of course, just the number of petabytes. If you just put it in petabyte scale, those are growing by tremendous amounts. That won't surprise anybody here, of course. Here's another example of microprocessor speed versus compact hard disk storage capacity, and then, of course, sequencing. And you can see, of course, the sequencing is going beyond the abilities of storage and microprocessors to keep up. That, again, shouldn't surprise too many of us. But as you'll see when I talk at the end of the day, I'm also quite interested in visualization, and that's, of course, another thing they talk about. And one quote in particular in this article caught my attention, where they say the creation of visualizations for complex data remains more of an art form than an easily conducted practice. And I think many of us would agree with that. Of course, people have tried to rectify this sometimes, even with what we would call inexpensive solutions. They show one of those here. This is projecting a result of different associations onto a large screen. So they use a projector like we're using here, but a much, much larger projector to project what's going on in their particular sophisticated data set. So it'd be much higher resolution than the typical display that we have here. But of course, it'd be much cheaper than, say, custom-built visualization systems like NASA Ames Hyperwall. So this is a 7x7 display wall, which I'll talk just a little bit more about at the end of the day when I talk about viewpoints. That's a custom-built system. Okay, it didn't cost a fortune, under $100,000, but still quite expensive. Of course, it can be used as a super resolution display like we saw here, but it can also be used to look at data sets in different ways. So in this case, you have a 7x7 display, 49 different nanotubes after identical compression experiments. So they take this nanotube and they distort it in a different way in each one of these. You can see how the atoms in that nanotube are distorted depending on what you've done to it. So you can look at data, multivariate data, in a very sophisticated way. Here's another one. This is from the San Francisco Bay Area. You can see that in black here. So they have sums of different channels above the diagonal and differences below the diagonal. And again, you can pick out different features in your data set that could be quite interesting. But again, that's more of a sophisticated but custom-built system. Again, as I said in the quote, more of an art form than anything else. But we'll talk more about that later in the day. But just to make sure that you don't think I'm a science chauvinist, I want to also say something that all of us are probably aware of, that data is also allowing new collaborations also within the humanities and between science and the humanities. I'm reading a very interesting book right now, Why the West Rules for Now, where this historian and anthropologist goes through and tries to figure out why he thinks the West is leading technologically, at least for the last several hundred years. And of course, he does this looking at history, sociology, anthropology, archaeology, of course, carbon dating, geology is very important for him, and of course, genetics. And all of this is made possible because of advances in all of these fields. So again, it's another example of interdisciplinary science and what it's capable of. So I won't drone on too much more. Here's today's schedule. Our next speaker is going to be Victor de la Peña from Columbia Statistics. He's going to talk about how long it will take, a historical approach to boundary crossing, and again, thank you all for making it here, and I hope we have a good conference. Thank you very much.